So today what I'll be talking about, in many ways, I'm kind of another atmosphere guy. So when I think of INM coupling, I usually think about the I component of that. And I'll be talking today about the upper atmosphere of Jupiter and sort of one of the big ones in the solar system and one of the puny ones, Titan. So I'll be going from both ranges. And I'd like to highlight student contributions by Austin Eggert, a graduate student at Southwest Research, or at UTSA rather, and Justin Dino and Robert Ryan, who have been working with me at Christopher Newport University. So again, I'll be talking primarily about Jupiter and about Titan. At both of these, the Jupiter code is currently being developed, so I'll be showing preliminary results, mainly benchmarking results we're comparing with other codes to sanity check ourselves. On the Titan model that I have is more mature, and I'll be simulating some rapid temperature variations that we see that can be considered due to magnetospheric coupling. And then I'll outline some future and ongoing work that we're doing. So first up, talking about Jupiter. So as Ingo pointed out, and I don't have to belabor the point much, the red curve here, so what I'm showing, whoop, I had a pointer, here we go. It's the top button, yeah. So basically we have an altitude versus temperature on the horizontal axis, altitude in the vertical. The red is the data retrieved from the Galileo probe, and the blue curve is what you get if you just run with solar heating only. And there's a significant deviation between what you can model without other energy inputs, and so this led the community to posit there's missing energy, and it's been termed the energy crisis on giant planets, and as Ingo pointed out, this occurs at several, if not all, of the giant planets. Let's see. So two mechanisms that have been invoked to explain this thus far has been magnetospheric heating or gravity wave heating. And playing to the audience here, I'm going to explore the possibility that it's magnetospheric heating. Although I want to emphasize that the possibility of waves doing this it's a large possibility, and this is just one mechanism I'll be talking about. So one reason for considering the magnetosphere as a likely candidate is we know that the Jovian magnetosphere is very large, it's internally driven, it's extremely strong. So it's a natural idea to think, well, a lot of this energy could be coupling back down and then perhaps driving energy into the upper atmosphere that could then be redistributed. And then here's the figure that everyone's seen 1,000 times. So coupling into the outer magnetosphere back down into the, whoops, am I kind of losing my pointer? Oh, wonderful, thank you. Okay, yeah, so the energy is going to get deposited in the high latitude ionosphere. And the idea is basically an idea that Roble had in 1988, where you have intense auroral activity. This drives flows from the high latitudes down into the mid latitudes. You're able to redistribute that energy. One challenge on the giant planets is the strong rotation has very strong related, can divert this energy away. So it can become trapped, or one possibility is that it could become trapped, but that's why we're constructing models to test these hypotheses. So just to give a little bit of sort of the heritage of the Jupiter codes, there's JIM, the Jupiter Ionosphere model, developed by Akeleos, and it's based on the full auroral class of codes. There was a follow-on Jupiter thermosphere general circulation model that my advisor, Steve Booker, developed. And it's also a 3D general circulation model based upon the NCAR family of codes. And the one I'll be talking about primarily today is the Jupiter Global Ionosphere Thermosphere model, which is the University of Michigan's non-hydrostatic atmospheric model, first developed by Ridley and modified for other planets by myself, and Steve Booker is in preparation. He's working on the Mars version of GITM. So the shorthand I usually use is JGITM for the code I'll be showing today. Currently, what we have in is we extend from about 250 kilometers above the 1 bar pressure level up to about 3,000. So just above the exabase, depending on what temperature you're at. We carry most of the major neutrals, hydrogen, and a smattering of hydrocarbons there. It is a non-hydrostatic model. We sort of inherit a bunch of our physics packages from the previous JTG CM. So hydrocarbon cooling down deep in the atmosphere. We have auroral heating that Denis first developed the model of, and we've parameterized that in the code. There is some mid-latitude heating by heavy ions. This was previously used in JTG CM, but I think Tom Cravens has published work that shows that this is probably not due to heavy ion precipitation. The simulations I'm going to show do have this in there, so there's a big caveat, and the main reason why I'm doing that is because I'm comparing with what Steve did before for the benchmark cases. And we also have simplified chemistry, just enough to get the ionosphere going, but it needs improvement, and that's what we're working on. Just a bit about, because I discovered this quite quickly, you can't do a spherical Jupiter. So we went to spherical oblique coordinates. And basically, at this point, you need to bookkeep, make sure that you are properly allowing your radial distance to vary with latitude, and allowing gravity to not necessarily be completely vertical, but now you have components that are off of your local vertical. And this is a plot. This is altitude versus latitude. What I'm showing here is the vertical resolution as a function of the local scale height. So the code has variable resolution in the vertical. And for the most part, we're down below about, we get about 5 grid points per scale height. So here are 2 pictures. This is on the right-hand side. This is Steve's. The left-hand side is Jay Giddham's, so the previous JTG CM. The biggest difference is that mine are in color. His are black and white. But we have latitude versus altitude here. Primarily, what I wanted to show was that using the same physics packages, we were getting with the previous code something around 1400 to 1500 Kelvin in the high latitude thermosphere, and the temperatures that we're getting out of Jay Giddham are somewhere around 14. So we're ballparking pretty well. So it seems like I should point out that this is a logarithmic scale here. So the way the temperatures are plotted, they look distorted relative so they're just not plotted on the same type of scale, which is why they look somewhat different. Now, if we slice the Jupiter code horizontally, so now we're looking latitude versus east longitude, so it's more of a weather map. You can see the influence of the auroral heating here in the southern and the northern ovals, and it's asymmetric here. I've tried to put some wind barbs on there, but for whatever reason, they weren't quite coming out as well as I would have liked. But again, this is at a constant altitude of around 900 kilometers in the atmosphere, and I'm just showing that the temperatures in the auroral region are roughly around 1100 kilometers, and then they cool down to about 800 into the mid-latitudes. And part of this, the reason why this is 800 is partially due to some of the heating we've assumed at mid-latitudes. But as Ingo pointed out, understanding the energy balance in the mid-latitude thermosphere is a definite area of active research. One thing I'd like to point out is the winds are not quite as strong as we found with the JTG CM. And also I ran out for around 60 to 100 Jovian rotations, but it turns out I might need to expand this closer to 300 or 400 depending on how the code converges. So these results, again, are preliminary and meant for benchmarking purposes, so stay tuned, and we will have more updates from the Jay Giddham code. One interesting thing that I found, and this may alter as the code runs, is that we naturally get a sort of banded structure. Now, I'm not claiming that this looks anything like the actual Jovian atmosphere. This is now altitude versus latitude, and these are eastward winds, so there flows east and west in the planet relative to the surface of the planet. Again, this structure might change completely by the time if we run it out to convergence. So while it's encouraging, I wouldn't put a lot of stock into it at this point. One thing I did just to benchmark how the code is doing relative to data was I extracted the temperature structure at roughly the Galileo probe, and so the model is shown here in black, again, altitude versus temperature now, and the red is the data taken from the Galileo probe. Again, it's encouraging, but it's still a work in progress. This is just the composition, just for completeness here, an altitude versus density profile for hydrogen, helium, and H2, or rather atomic hydrogen. And we're working to, currently I'm working with Tariq to input a much more improved H2 chemistry into the model, which is very important for the ionosphere. So sort of the big takeaway is it looks like the magnetosphere is inputting sufficient energy to redistribute energy to the low latitudes, but there are also processes in there from the JTGCM that we need to examine. So encouraging, but needs a little bit more time before it's ready for prime time, perhaps. I'd like to move to an extremely small planetary body, Titan, in many ways sort of the opposite of Jupiter, slow rotating, thick atmosphere, and quite small. Titan's atmosphere is quite interesting because it's probably the only other substantial atmosphere well, it is in our solar system. And then with that nitrogen, you have a smattering of CH4 and H2. What's fascinating is the possibility that it's an analog for early Earth, and so you're possibly having the chance to look at Earth at a stage before significant oxygenation occurred, and it makes it, at least that's a good selling point, right, when you're talking about wanting to study Titan. Hopefully Titan can inform us about Earth's own evolutionary trajectory. So what I'm going to show are some interesting observations from the Cassini mission using one-dimensional and three-dimensional versions of the Titan GITM code, or Titan Global Ionosphere Thermosphere model. So just briefly, I don't want to go through a lot of model speak, but T-GITM, like Earth GITM and Jupiter GITM, is non-hydrostatic, only now we're going from kind of the base of the thermosphere up to 1,500 kilometers above the planet, so it's a very extended atmosphere, which is roughly the exobase, so we're kind of covering the mesosphere up to the exosphere. We include energy chemistry and dynamics into the code. And what I want to show is that MI coupling at Titan could explain a lot of the rapid temperature and density variations that we're seeing at Cassini. So I think these figures were shown in previous talks. Titan is sitting right here inside of Saturn's larger magnetosphere and resides within the magnetosphere for most of its orbit. There are people here that think about this a lot more than I do as far as its location. And this is kind of the canonical schematic of how Titan would interact with plasma and field lines coming in. But one thing that Joe Westlake investigated was the fact that the local plasma, the intensity of the local plasma, seems to have important impacts on the neutral density structure at Titan. So I probably don't need to go into this because other people had talked about it. This is just a picture of Cassini and a sample of the ion neutral mass spectrometer data, INMs. And so we're taking in situ measurements above 900 kilometers in Titan's atmosphere. And it's been sampling since 2004, and I guess we now have something like 98 flybys. I forgot the number that we actually have. But unfortunately, due to mission constraints, the coverage is sometimes sporadic in time and in space. So we don't get global coverage. You get slices every now and then, and you try to piece together what you can. Now, what I'm showing here is some INMS data that was published in Westlake et al. 2011. I should have had a reference here, but it's missing. So this is altitude and neutral density, nitrogen density rather. And what Joe went and did was look at the intensity of the plasma environment. So the red dots and curves are during the plasma sheet, or more heavier, a dense, hot plasma. And then the black represents more lobe-like conditions, a low intensity, low energy input plasma. Basically let's see if I can get it to pop up. Basically what we found was that there's something like a 30 Kelvin difference between these two profiles when you're trying to match it with a model. And another way to look at this is these are now temperatures, the mean temperature of each flyby, and these are now days. So each one of these is a different Titan encounter. And temperature is on the vertical axis, so you can see there are warmer flybys, and there's a lot of variability in through these different flybys. Some of these are just 16 days apart, and some of them are over the same geographic area. So you fly by, and then you come back another orbit later, it's almost the identical geographic area, and you see rapid temperature variations. So again, this is just to show it again. This is Joe showed that the mean plasma sheet was something around 144.7 Kelvin, the temperature in the atmosphere, and the lobe was significantly colder at 120. So it's a significant variability. And so, I basically just said that in words. So what we did was we took T-GITM, and we ran it in both 1D and 3 to test this out. So what I did was I set up a numerical experiment where I looked at a 1D column and let it rotate with the rate of the planet. So it would be what you would observe if you were staring up at the thermosphere and you were stationary on the planet. You would see a diurnal variation. So what I did was I ran the code without any plasma heating. So you can see this is down here, the contours, this is altitude and this is time. So on the horizontal axis, all of these are time. So what I'm showing in the contour plot is now a vertical profile. So you can see the contour values are temperature that probably kind of it's kind of fuzzy, I apologize. But here is the cold nighttime, warm in the day, cold in the night. And so it continues with this diurnal variation. We kick on a plasma pulse, basically a square wave plasma pulse, and then we end that pulse, and we watch the atmosphere return back to its old diurnal variation. But when we kick on the pulse, you can see that the peak occurs right after the integrated heating has had an effect. And what we can do is we can slice this through time, so the solid black and the dashed black are shown here. So this is now temperature over time. You can see the diurnal variation, and then we hit this first plasma pulse, and then it warms up significantly, and when it cuts off, it comes back down and recovers to its variability again. So at least within this kind of numerical thought experiment, it seemed like plasma heating could possibly explain rapid variability in the upper atmosphere. So the natural extension would be the 3 dimensions. What I'm showing here, I tried to put everything on one color bar, but I'm not going to do that for the next plot, so I'll show you something that has a little bit more structure to it. So bear with me on this one. I have 2 simulations here, so if you slice this in half vertically, this simulation has only solar heating in it. The one on the left, we've included a kind of orbit average plasma heating. Now this heating is assumed to be constant, so it's not varying, which is, as Ingo mentioned, steady state solutions aren't necessarily realistic, but this is, again, a numerical experiment. So what I'm showing on the top is right at the exobase. I'm slicing it horizontally. So this is latitude and longitude, so it's a map right at the exobase. These 2 bottom panels are like the equivalent maps, but now deeper in the thermosphere, so at around 960 kilometers. The net result here is that the solar heating only case, so both high and low altitude, are colder in general than the ones where we include plasma heating, which isn't a huge surprise. So if you look at these in a different way, with more structure, each one has its own color bar, you can see that, again, you can see similar structures between them, but we've had plasma heating input into the model, and that's significantly shifting the peaks and the troughs of the energy. One thing I'd like to point out is I've been showing solar local time, so these are the same format, longitude versus latitude. And T-GITM simulates the coldest area in the exobase is right at noon, and the warmer areas are in the polar regions and on the terminators, which is similar to what we see at Mars. When you're forcing it underneath, you push energy up, it flows go up and then diverge in the exosphere, and you tend to have a phenomenon called winter polar warming or thermospheric polar warming, and this is very consistent with that Mars type structure. One thing that in the data we also see that this is now, just to draw your attention to these 2 red lines, both Joe and Jun Sui have pulled out day side and night side temperatures at Titan, and it does have a colder day side versus a night side, so it's good that we're capturing the general structure, but the magnitudes aren't necessarily perfect. One more aspect of the MI coupling is that it also, if you engage ion transport, you can significantly alter. This is the same structure again, so this is now latitude and longitude, and these are ion densities. So when we allow the ion densities to flow in the model with winds from MHD models, we can significantly alter the ionosphere and the resulting chemistry and energy balance. So we have a lot of work to do at Jupiter, so we want to improve the ionospheric dynamics, improve the heating, especially get a more realistic mapping of heating down into the thermosphere. working with Tariq to improve the chemistry, and we really want to look at the potential wave activity coming up. I didn't talk about this mainly because it's an MI coupling session, but our goal is to get everything ready for Juno, and I think we're on track to do that. We're also working to convert this to a Saturn GITM, especially for the end of mission and interpreting INMs data as we go in. And I would like to say Alex Glosser should totally couple PWAM with JGITM and SGITM. So that one was for Fran. I don't know if she's in the audience. At Titan, we're currently working to couple the Titan model with Yingzhuan's MHD code and Ilka Salampa's hybrid code, so we'll have improved energy deposition over time. We're also examining waves and tides that Darcy Snowden has made the case are important. And we're starting that with a student, Justin Deno, who's going to be looking at the gravitational influence into Titan. And I would like to do one quick thing if I could pull this up real fast. I would like to show, I don't know, oh, it's not quite coming up well. Oh, maybe I could just skip it. It was going to be a movie that showed the plasma response, but it's not quite working, so I'll just skip that. But yeah, oh, whoops. It was not doing it. Anyway, thank you.
Actually, I have a It is, okay, it is red. But yeah, I have a terminology question and a more speculative one.
Sure.
When you say non-hydrostatic, do you mean hydrodynamic?
So when I say non-hydrostatic, I mean we solve the vertical momentum equation. So we have 3 full momentum equations instead of assuming hydrostatic.
With time derivatives and everything.
Exactly,
right?
yeah.
And the other thing is well, you mentioned a little bit about gravity waves and things like that at the end. And maybe this is just totally crazy, but of course there's all these big storms in Jupiter, like the red spot and all that sort of stuff. Does any signature of that propagate up into the upper thermosphere?
To be honest, I don't know. I haven't tried to input anything like that. Ingo, have you seen anything like that at other planets coupling? Okay. Yeah, because that's a great idea. I mean, we know there's a lot of turbulence and a lot of churn down there, so you would think it would conduct up.
Okay, Jared, and this is sort of in a way to Ingo as well, seems to be a real problem with these models that we don't have at Earth is you don't have wind measurements.
Yeah, that's true.
I mean, which, you know, you're worried about the circulation getting down to lower latitudes, which on Earth gives you that adiabatic heating, and on Earth we have this stuff, so that's going to be crippling even into the future, you know?
There are wind measurements at high latitudes.
Oh, the H3 plus,
The
yes,
H3 plus,
but not down in the mid latitudes, you know, where your problem is.
Just really quickly on that, I was just going to mention that we are starting to pull out ion winds out of the IBS, which you would assume for Titan are going to be very close to the neutral winds in that case, in the low altitudes. Yep.
Jared, you had a diagram you called a weather map,
Right.
longitude versus latitude. It was in Jupiter longitude, and there was very strong longitudinal variation. What does that come from?
Let me see if I can pull that up for you real fast. This one right here.
Yeah, but I don't, yeah, well, there is strong longitudinal variation at high latitude. What produces that?
So when I've input the auroral footprint from Denise code in there. So there's a longitude varying auroral oval, which I probably should have put up there, but it's kind of a map of the auroral footprint. And then the heating rates come into those areas, and I think that's driving the inhomogeneities there. So it's not. Yeah, I believe it's just, yeah, that's exactly.